Welcome to ePathshala lecture series. We are discussing about cryptography and network security. In this module, we are going to discuss about RC4. Objectives of this particular topic: to understand Verman one-time pad and discuss about random number generator and its property, and also we are going to discuss about stream cipher and RC4 algorithm. So, before going to discuss about this RC4, we need to understand what is this one-time pad. During the stream cipher and block cipher, we have listed out some of the algorithms which are related with real world application. So, before going for that particular algorithm, the initiative was done by this one-time pad, usually called as Verman one-time pad. It is developed by Gilbert Verman in 1918. So, where we usually call Verman cipher. So, this is the first step towards the development of all the modern cryptographic algorithm. Here they use encryption and decryption very simpler manner with the operation of XOR. As in the case of your stream cipher, it is also category of stream cipher algorithm, where the C suffix I, that is your ciphertext, is generated a stream of Mi XOR of Ki, where I is equal to 1, 2, 3, 4, etc. Similarly, as you see in the decryption, where you can able to get back your original message, that is your M suffix I is equal to Ci of XOR of Ki, where I is equal to 1, 2, 3, 4, etc. So, now the property, as you know, the XOR operation, when both the inputs are 0, we will get 0, or else if both the inputs are 1, we will get 0. If any one is 0, other is 1, we will get 1 as the output. So, using this particular property, here this values are cancelling each other and getting back the original message. So, the key is a truly random sequence of zeros and ones. When you are looking into the classical cryptography, we used only the alphabets A, B, C, D up to Z. Any one we use for doing the modulo operation to generate the ciphertext. But this is the first algorithm which the keys are truly random sequence of zeros and ones and the same length as the message with respect to our stream cipher, and also it is having the property of one time only. It is using one time only, as we know, where if we are using the key again, there is a chance of an attacker to get back the original message, or he can able to derive the key, as we say there is a low in the case of your diffusion or confusion in the case of your stream cipher. The encryption is adding the key to the message modulo 2. Why they are using 2 here? Because every message is considered as either a 0 or 1, that means bit by bit. In stream cipher you are taking a byte stream, even though it is a byte stream, we take a series of zeros and ones. In Verman cipher it is considered as bit by bit, so it is taking the modulo of 2. When a message is going to be added with K, that is your key, it is generating the cipher C of modulo of 2. Now, we will see an example with respect to your Verman cipher. Here is the plain text. Suppose a person want to send a plain text to a B, person A want to send a cipher text to a person B, he need to choose the key as series of zeros and ones. Now, they do an XOR operation. So, when they do an XOR operation, so we will say that if it is going to be 0 1 0 1 0 1 1 0 1 0 0 0, and then we will get 0 1 1, like that. When both the inputs are 0, if both the inputs are 1, we will get 0 as the output. whereas if either one is 1, will get 1 as the output. So, both the inputs are 1, both the inputs are 0, you will get 0 as the output, whereas any one input is 1, will get 1 as the output. Now, we got the ciphertext. This ciphertext is going to be sent to the receiver, where he is able to generate the plain text same XOR operation. But here we have a practical problem. So, what is the practical problem here is the key stream should be as long as the plain text. So, when I am choosing the key, as you look into the example, where you can see that if there is 16 bit, I need to choose 16 bit key. Practically it is not possible. Your message may go even more than megabytes, then it is impossible to choose a key, and difficulty in key distribution and management. That means when I want to share the key with the receiver, it is very difficult how to get into the particular user. So, what is the solution here? How to overcome the problem faced Verman cipher? The solution is stream cipher. Stream cipher, I am not going to have a key as long as the size of your plain text. Instead of that, we will have an initial key as we discussed in the stream cipher, and the remaining things are going to be handled by the property of pseudo random fashion from the relatively short secret key. That is what we discussed with respect to your stream cipher, where I choose a key and then with the help of pseudo random generator, and also the key is short secret as compared with a long plain text. As compared with your long plain text, it is going to be a short secret key. So, there is no problem in distribution and management of key as we face in the case of your Verman one time pad. So, we already discussed about this in the stream cipher, where it will have one state function, another one is your output function, and all the states of your receiver at a time is stored in the state. So, based on that, it is going to be generated in the stream cipher model. So, what is this random number? Because this plays an important role in the stream cipher. So, we need to understand the random numbers before proceed with your RC4 algorithm. Many use of random numbers in cryptography, where lots of places we come out with the random numbers. For an example, if I take a nonce, generally we say nonce means number used once. Usually it is used as an initialization vector. Even in the case of your block cipher and also key distribution, most of the cases we come out with this nonce, and the session key, which is also generated based on your random number, public key generation, key stream of one time pad, all these cases we come out with the use of random numbers. So, in all cases it is critical that these values should be statistically random and uniformly distributed independent. So, when I am going to design a random number generator, a pseudo random number generator, a random number generator or random number to be used in your algorithm for generating the key, you should be having the property of statistically random, uniform distribution and independent. That means there should not be dependency between one random number and the other random number. We cannot able to predict how they were related, how they can able to derive from one random number to another random number, and is unpredictability of future values from the previous values. That is what we told. So, unpredictability. When I take one random number, in future I should not guess, maybe this pattern may occur for the generation of the key. So, it is necessary to generate, it is necessary to take care during the generation of your random numbers. So, in this case we are using a pseudo random number generator, that is often using deterministic algorithm technique to create random number. So, why it is called pseudo random number generator is, although are not truly random. So, it is impossible, it is very difficult to get the random numbers with the help of an algorithm to generate different patterns. So, instead of that we use some deterministic technique to create a random numbers, but it is not truly random, but it can pass many tests of randomness. So, it is known as pseudo random numbers. So, usually these are generated with the help of your PRNGs, that is your pseudo random number generator. So, why it is pseudo random number generator? Not truly random, but definitely it may pass the test of randomness. So, how these generators are able to give the random numbers or pseudo random values? So, with the help of this particular structure. So, source of true random diagram, that is your true random number generator, that is source of true randomness, conversion to binary where it will be a random bit stream, but actually we are using this pseudo random generator where it is using some deterministic algorithm with the help of some seed values, seed input. So, automatically the process is going to be giving some pseudo random bit stream. Then if I want to have a pseudo random value seed with the help of your specific context specific values. So, actually here we are going to use this pseudo random bit stream for generating your key stream. So, what are the requirements if I am going to choose the pseudo random generator? As I already mentioned the property with respect to your random numbers, here also it should have a randomness, that means uniformity, scalability and consistency. Unpredictability, that means it should have the property of forward and backward unpredictability. So, we cannot either get the future value or the previous value from the known value. Use the same test to check. And also characteristics of seed, that means as we have seen here the seed value, the characteristics of seed, it should be secure. So, nobody knows about this seed, what is the initial value used for generating the pseudo random number, and if known adversary can determine the output. Suppose it is not, if the seed is known to the attacker or adversary, they can easily determine what is the output. So, it should be kept secured, the seed. So, must be random or pseudo random number. Again it should also have the property either a random or pseudo random number. So, how, where you come out of this pseudo random generator in the case of your block cipher, because not only in the stream cipher, it is also playing an important role in the case of your block cipher algorithm like your DES, AES, triple DES algorithms, where we know about this modes of operation. That means during the generation of your encryption, that is your ciphertext, during the generation of your ciphertext in the encryption process, they are basically used one of the mode of operation called CTR, counter, another one is OFB, output feedback. So, in this case this is used as a initialization vector, IV, initialization vector for generating the pseudo random bits. So, for cryptographic calculation can use the ciphertext to generate the random numbers, often for creating session key from the master key. So, under the stream cipher we already discussed about this, it should be an one time pad, generalization of one time pad, and cipher, stream cipher is initially with short key, and also it is stretched to long stream key, that is key stream having the property of pseudo random property. Then key stream is used as one time pad, that is where XOR is used for encryption and decryption process. So, now we are coming to the RC4, it is one of the example for your stream cipher algorithm. It is named after the person who invented this algorithm for performing an stream encryption, that is Ron Revest. Actually it is R for Revest cipher, Revest cipher 4 version 4, that is why it is named as RC4 algorithm. A symmetric key encryption algorithm is invented by Ron Revest, a proprietary cipher owned by RSA kept secret. The code released anonymously in cypherpunk's mail list in 1994 and later posted in science.script news groups. So, it is a variable key sized byte oriented stream cipher. So, normally this algorithm is more popularly used in the case of our HTTPS services like your web browser and the server, where they use an SSL and TLS secure socket layer and transport layer security to encrypt the data between your web server and the client. Apart from that, it is also used in the case of your wireless LAN like your WEP, wired privacy, wired equivalent privacy, and WPA, that is Wi-Fi protected access. So, this algorithm was used till date with respect to our WEP, WPA, but no longer supported by SSL and TLS due to the weakness behind the internal design of this particular algorithm. So, normally you can able to see it use 64-bit and 128-bit key size to generate a ciphertext with a variable key size bit oriented cipher algorithm. So, as some of the list where we can able to come out with the usage of this algorithm is WEP, WPA, bit torrent protocol encryption, Microsoft point to point encryption, SSL, SSH, remote desktop protocol, Kerberos. So, it is used in most of the algorithm, most of the applications. Now, we are coming to the block diagram of RC4. I think we are familiar with the stream cipher. Now, we can able to see the same structure is also used in the case of your RC4 block, RC4 cipher algorithm for the encryption process. So, one thing there is a change here is we can able to see here is an RC4. So, earlier in the stream cipher block we have seen that it is given by the pseudo random generator. Now, the algorithm plays a critical role for generating of your key stream. So, I think now we can able to understand here it is adopting the same structure of the stream cipher, only thing is here it is using the RC4 for encryption. So, the working of the algorithm we need to understand from this particular block, whereas the other things are similar as we discussed, where you have a secret key and the plain text are going to be encrypted, give a. So, cryptographically it is very strong and easy to implement, only thing is we need to understand what is there inside this RC4. So, inside the RC4 there consists of two parts, one is your key scheduling algorithm KSA, another one is pseudo random generated algorithm. So, these are the two components or two important parts of your RC4. One is your key scheduling algorithm, another one is pseudo random generator algorithm. So, here KSA used to generate state array. So, when I take the initial key, that is your secret key, very short key, when compared to your Verman type pad, it is using only smaller key as a secret key. From this key, this RC4 is going to generate a state array, and the pseudo random generator algorithm on KSA, it generate key stream, and this key stream is further used for encryption of your message. So, now we will see that how this key stream is going to be generated. To generate key stream, here we have secret internal state which consists of two parts. So, before going to know about this KSA, we should understand this, a permutation of all 256 possible bytes and two 8-bit index pointer denoted as I and J. So, there will be S, I and J. These are internal secret state for the generation of your key stream. We know very well, in your stream cipher we use message stream, that is your message byte stream, key byte stream to generate your cipher byte stream. So, I want this key byte stream or key stream, for that I need to use some secret internal states. This is based on the permutation of all 256 possible bytes and also 2 8-bit internal pointers. Now we will see that key scheduling algorithm. As we mentioned earlier, there is an internal secret state. So using the secret key, this is given by the user. For example, A want to send a message to B using RC4 algorithm, first they must agree with the secret key. So now I have a secret key to initialize and permutate of the state vector S done in 2 steps. So I want to go for state vector. I should get the state vector. So there are 2 index pointer, one is I, another one is J. So here I is equal to, in this particular part, the first part where we have for I is equal to 0 to 255, do S of I is equal to I and T of I is equal to K of I mod K. We know that K is the key length, the length of the key actually is an array byte of your secret key. So the initial key which is used for encryption, it is used between the user A and B. Then we have a S is set equal to values from 0 to 255, that means S0 is equal to 0, S1 is equal to 1, like that S255 is equal to 255, and there is a temporary vector. So now for inside this for loop we are going to do this S of I is equal to I, that means S of 0 is equal to 0, S of 1 is equal to 1, and from that we are going to have a temporary vector. This is our temporary vector which is based on the secret key. Then here I will go for using this temporary vector, that is T, to produce initial permutation of your S. For I is equal to 0 to 255, do, where J is already we know that is an index pointer J, where J is equal to S plus J plus S of I plus T of I mod 256, that is permutation of 255. The only operation S is swapped, that means here it is going to be swapping, S of I and S of J are going to be swapped, and still it contains a number from 0 to 255. After this KSA, the input key and the temporary vector T will be no longer used. So from this I will get S, right, I will get the permutation of state vector S, then the temporary vector and the input keys are no longer being used for the encryption. Now we are coming to the pseudo random generator algorithm. This generate key stream K one by one. Now looking into this block, here it is using encryption and decryption. Already we know there is 2 pointers J and I and J. Suppose more bytes to encrypt inside this while loop, where you can able to see that the swapping of S of I comma S of J, okay, that is where you can able to see that this swapping is sum of the shuffled pair selected stream key value from permutation, shuffled pair selected stream key value from the permutation, the purpose of this. And after that we generate the key stream one by one, that is K is equal to S of I plus S of J mod 256, and once it is done we got the K, that is your key stream. From that we can able to generate the ciphertext where your M is the message XORed with your S of K. So this is your encryption process. So for that we need to get this particular key. So it is done with the help of your pseudo random generator algorithm. So using this pseudo random generator algorithm I got the key, that is your key stream one by one, and it get converted the plain text to the ciphertext. As we look into the diagram how this swapping of your S of J S of I is done. Suppose I am taking the state vector 0 to 255, S of I and S of J are combined to generate a K. This is what the diagram. So here it is, you can able to see that the output byte is selected by looking up the value of S of I and S of J, adding them together modulo 256, then looking up the sum in S. This is your internal state. From this internal state, I know what is S of I and S of j, then we are combining these two, I will get the k. This k is now becomes our, so and this k is used for encryption. This is the detailed diagram which is going to be explaining how the stream is generated at each and every stream with respect to your KSA and pseudo random generator. The overall process of your RC4 as an example for your stream cipher, we can able to understand this state and key initialization. It is done only once, that is during the initial step of your algorithm. Then we have permutation, this is also done only one, right. So, here it is mixing with the key bytes and permute for getting your state, and once it is done, we can able to see that the process of encryption with the help of your stream cipher, plain text and your key 8-bit XOR to get the 8-bit cipher text. This is the first byte, second byte till the end of your message. So, this explains the overall operation of your RC4 based on the stream cipher. Decryption is very simple with respect to your encryption. Use the same secret key during the encryption process. The generated key by running the same parts, that is components, one is KSA, that is key scheduling algorithm, and pseudo random generator algorithm. They are using the XOR operation. It is very simple logic that you can able to see that if suppose I am taking a message M is as A plain text, B as the K, that is your key. So, A XOR of B XOR of B, B and B get cancelled, I got the plain text. So, it is the very simpler process, the encryption decryption, but the key component of your algorithm is mainly based on the generation of your key string. Okay, now we are coming to the conclusion. So, from this session we are able to understand what is Verman one-time paired and how it is initiated for the random number generation, what are the drawback, and finally we understood the stream cipher. One of the algorithm belongs to stream cipher is RC4, how it is used for encryption and decryption of your plain text using the key stream. Thank you.